Welcome to Mathematics with Tom. I am Tom. Today we're going to be looking at section 1.4 in our textbook, and what that is we're going to solve the differential equation y prime equals ay plus some function q. Remember, all these are functions of time for q a constant function. Q is a constant function. So it could be 5 or something like that. All right, now in our previous video, and so I think, actually let me go back. I think that we're going to do this two ways. The first way is this. We said that our general solution is that y of t equals e to the at y times y of 0 plus e to the at times the integral from 0 to t of e to the minus as times q of t. But now q is some function, is just a constant function, so we'll just call it just q, not a function of s anymore. So that just becomes this integral here. Well, we can integrate this. So this is going to be, there we go, yeah. So we have e to the at times y of 0 plus, this is going to be an e to the at, and I'm going to just bring that q out, so I'm going to put times q. Now the integral, this has become, let's see, we're going to have to divide by the a, so it's going to be minus 1 over a times e to the minus as, and we're going to evaluate that from 0 to t. Okay, so we have e at y of 0. We'll just leave it like this, plus e to the at times, times we're going to have a minus q over a times e to the minus at minus, now we're going to plug in a 0. Well, when I plug in the 0, that's going to be e to the 0, which is just 1. And now let's do a little bit of cleanup. I'm going to factor out the minus. So if I have e to the at y of 0, then I'm going to have a plus. Okay, and now we're going to do a couple of things. Let's distribute e to the at. And we're going to distribute this minus sign. Well, you know what? That's too much. That's silly. I don't need to do all that at once. Let's just do this one little bit at a time. So we have plus, we'll write this as q over a times, so when I distribute the minus sign, this becomes a 1 minus e, oops. I was getting so excited to see this coming together. All right, slow down here. So then I'm going to just change these and become 1 minus e to the minus at. Now, here we go. E to the at times y of 0 plus, we have a q over a. Now when I distribute e to the at, I'm going to get e to the at, and then an e to the at times an e to the minus e to the at, that's just e to the 0. Well, that's just going to be 1, so I have a minus 1. And there it is. This is the solution to the differential equation for q being a constant input function. There's our solution. Now, let's see what happens here. What does this mean? And I think the best way to look at this is with an example. So let's look at an example. But we're going to have to do two. Example. So let's look at the problem of y prime equals 2 e, 2 times y plus 3. Okay, there we got numbers that we can keep track of. Now let's just plug these numbers in. No, I think I've got everything set up right. So then this says my solution is going to be y of t equals e to the at, so it's going to be 2t. Notice in this case, a is going to be 2 and q is the 3, plus q over a, so that's 3 over 2, times e to the 2t, e to the 2t minus 1. And there it is. Now I can clean this up a little. We could combine some like terms. We could have e to the 2t plus 3 over 2e to the 2t minus 3 over 2. And then I could add my e to the 2t's. This is 1.5 plus 1 more. That's a 2.5, or 5 halves. E to the 2t minus 3 over 2. Okay, so let's try something here. So where does this function begin? So where does it begin? Well, if I plug in my y of 0, what am I going to get here? I'm going to get e 5 over 2, e raised to the 2 times 0 minus 3 over 2. Well, that's very simply e to the 2 times 0, that's e to the 0, that's 1. So this is really 5 halves minus 3 halves, that's 2 halves. This is just 1. So this equation starts at 1. So if I was to make a quick sketch, I have a function that's starting here at 1, and it has some constant input. Now think about this. Even though you have this minus 3 halves, e to the 2t is going to grow so fast that your equation is going to just go up like this. Okay? And so we say that our author calls this y of infinity, so y of infinity, or sometimes just writes y infinity. In this case, it just equals infinity. So this is also called an unstable solution. It just grows. Now, hopefully, that's your bank account, and this is your financial portfolio, and it is just growing wildly by exponential continuous growth. Now, let's take a look at another example. So here's what we have. We said that y of t is equal to e to the at times y of 0 plus e to the at times the integral from 0. Our final solution, e to the at, was not that, plus q over a times e to the at minus 1. Okay, that was our general solution when q is a constant function. Q is constant. Okay, so now let's look at this. Let's look at the problem of y prime equals minus 2y plus 3. And let's see how does that change this problem. All right, so let's substitute these back in. So I have y. So this says y of t equals e to the minus 2t. Oh, let's do this. And we're going to we'll start this problem, y of 0 be, how about 4? There we go. So e to the minus 2t times y of 0, that's 4, plus, then we have a q over a, that's 3 over negative 2 times e to the minus 2t minus 1. Now let's clean this up. This is going to be 4 e to the minus 2t. This is going to be a minus 3 over 2e to the minus 2t plus 3 over 2. Okay, well, what does this say? Oh, let's combine these 4, which is 8. This is going to be 5 over 2 e to the minus 2t plus 3 over 2. Well, let's look at the end behavior. The end behavior. Where is this equation going? End behavior. And our text uses the notation y infinity, which is really, imagine if you went out to some really large numbers, what does our equation look like? Well, in this case, as t approaches infinity, what happens to e to the minus 2t? Well, that becomes 0, and it becomes close to 0 very, very fast. So what I can say is that my end behavior is y infinity is going to equal 5 halves times 0 plus the 3 halves. Well, that's just 3 halves. So what do we have? Well, let's see. This says then we have our equation. Here's our graph. And we have 3 halves. So let's put here's 3 halves. Okay. And notice that this problem is going to start at 4. It's going to start up here at 4. So put 4 right there. This equation is going to start at 4. And then what it's going to do is it's going to just head back down. And that's going to be the bottom of my exponential function. And at this point, what we know also is that it's going to be, when we get to 3 halves, our derivative, notice that this would indicate a flat curve. Well, is there another way to see that? And the answer is there is. Look at this. This is also the idea of, well, when the curve is flat, then the derivative is 0. Well, y prime would be 0. But what is y prime? That's the initial problem. That's minus 2 times y plus 3. And if I solve this, then I get y equals 3 over 2. And that's where that limiting function, this limiting value of 3 halves is where, if it could happen, that the curve would actually become flat. And we've already seen the picture of the curve of e to the minus t, and it doesn't ever swoop down. But remember, the reason that I'll do this in this corner, this is the wrong. We know that this is wrong and it doesn't do something like this, is because if this was the case, then that means right there it would have had a derivative of 0. So that means that it can't dip down and then come back up. It means that it just has to come down and just get closer and closer as time goes further and further. And that is how you look at these behaviors. And we call this, this is a stable solution. A stable solution means it has some ending value. And you hope that if you're investing in some kind of count your money in some account, you hope that it doesn't have a stable solution. You would hope that this would describe something else. Hope that helps. Thanks for watching.